Welcome to semester one final review video for regular physics. We're going to be covering 1D kinematics, 2D kinematics, and forces, which is all the physics stuff that you learned this year. I'm not going to cover scientific analysis or stuff like that because that's not strictly speaking part of the physics content. So I'm just going to go into that part. So let's get started. First of all, a few key terms you need to know. Time reading or clock reading is basically a position in time, like a location in time. For example, 2 seconds, 0 seconds, 5 seconds. And time interval, on the other hand, is the change in time. So while time reading is given by this, time interval is delta, and the delta means change. So it's the change in time reading, or it can be like 2 seconds because it went from 0 to 2 seconds. The time reading first was 0, then it was 2, so the time interval is 2 seconds. We've got position, which is usually represented with an X or S or something like that, or Y and Z if you're talking about other dimensions. And the reason why we use these is X, Y, and Z are the dimensions, and S is just arbitrary variable for position in general. Position is going to be a location in space, while time is a location in time. So it'll be like 2 meters, or in a bit, we're going to talk about vectors when we talk about 2D motion. So you can have a vector that's 2, 3 that represents a position. There's also displacement, which is the change in position. And I'm only going to use X for this one because since there's 4 variables, I'll just use X for displacement. It's going to be the change in position, final position minus initial position, and not to be confused with distance. So distance doesn't really have a symbol, but it's going to be the total motion of an object. So the reason why they're different is, let's say there's a point here and a point here. Displacement is going to be this no matter what, because that's the change in position. That's the original position, that's the final position, so it's the change in position. Distance, on the other hand, can be something like this. You go anywhere you want and then end up here, and it's going to be a total sum of all the motion. While displacement is just this, and you can see how they're vastly different. In fact, distance can be like this, while displacement is still 0 because the final position is the same as the initial position, which is why displacement and distance are not exactly the same, but the general rule of thumb is in this kind of physics, displacement and distance are related because distance is always going to be the absolute value of displacement. That's not always the case, like I showed you here. But what they're highlighting is the fact that displacement has a direction, but distance does not. So moving 10 meters this way and 10 meters this way are the same for distance, but different for displacement. Finally, there's 3 more quantities. Velocity is V, and it's going to be the change in position over change in time, or basically the displacement over change in time. Displacement over time interval. A bunch of ways you can see. As you take calculus, you learn about instantaneous velocity versus average velocity. So average velocity is going to be over some time, while instantaneous velocity is going to be at a single moment in time. And we'll get into that in a few minutes with velocity time graphs and displacement time graphs and acceleration time graphs. There's also speed, which again does not really have a symbol, so I can't write it down, but it's going to be distance over time. So people also regard speed as being the absolute value of velocity. And finally, there's acceleration. Acceleration is the change in velocity over change in time. And again, there's instantaneous and average acceleration that we'll get to in a minute. But the reason why position, velocity, and acceleration are related is because, as we'll see in a minute, their graphs are very related to each other. Moving on, finally, we're going to talk about the graphs. So there's 3 main types of graphs. Displacement time graphs, which is xt graphs. Velocity time graphs, which are vt graphs. And acceleration time graphs, which are at graphs. So how do these relate to each other? Let's say xt has an equation x squared, or in this case t squared, since time is the independent variable. What would velocity be in that case? So if you took calculus, you would know that velocity is actually what's called the derivative of x, or position. And what that basically means is the velocity determines the slope of x. So a little bit easier to understand, if you have x, um, oops, if you have xt and you have a simple line, the velocity is going to be the rate of change, because velocity is the rate of change of position with respect to time. So rate of change is another word for slope, meaning velocity is just going to be the slope. And if you have that, velocity is just going to be straight line, since the rate of change is constant throughout the graph. And then acceleration will be zero, since the rate of change of velocity is zero throughout the graph. But what if we had a quadratic? That's where calculus comes in. And you learn that the derivative of a quadratic equation is going to be a linear equation. Now, regular physics isn't that calculus oriented, so you're not expected to know calculus, but it's important to know that a quadratic position graph correlates with a linear velocity graph, which in turn correlates with a constant acceleration graph. Then we have, what about the other way around? If you take the slope to go from position to velocity and take the slope to go from velocity to acceleration, what about acceleration to velocity and velocity to position? That's area under the curve, or integrals in calculus terms. So that's going to be the integral here, or the area under this curve is going to give you the velocity, and the area under the velocity is going to give you the position. And you can do some calculations with that and create a position graph given a velocity graph or whatnot. Um, that's mainly it for the descriptive part of 1D kinematics. And then there's obviously equations we need to know. You do get an equation card, and you probably should have been updating that equation card for a while. So I'm just going to review some of the most major equations for 1D kinematics. So the first one is going to be when you have no acceleration, you have displacement is equal to velocity times time. You only use this when there's no acceleration. And this should actually be time interval, because it's a change in time. This comes from the fact that velocity is the change in position over change in time. You just multiply both sides by the time interval, and you get displacement is equal to velocity times time interval. This is when there's no acceleration, because if there's no acceleration, that means that the average value and the instantaneous value of velocity would be the same no matter what. Now, for the equations that do have acceleration, one of them is position, or displacement change in position, is going to be equal to initial velocity plus final velocity over 2 times t. Let's break this down a bit. Initial plus final velocity, that is going to be average velocity, because it's the sum of the first and last terms divided by 2 that gives you the average. Now, the reason why we're using average is because we cannot use instantaneous, since we don't know calculus, and since there's acceleration, meaning instantaneous velocity changes. So we have to use average value. One thing I do like to point out is that I'm going to write no A over here, and you might be a bit confused because there is acceleration. But, or actually I'll write without A. The point of this is that this equation does not use the variable A. And that's a key thing, because later on, you're going to do word problems where you're given like a few of the variables. You want to find one variable, and then one variable is just not mentioned at all. In this case, if acceleration is not mentioned at all, you use this formula, because this formula does not have acceleration in it. There's still acceleration in the problem, but acceleration is not given and does not want to be found. So you would use this equation in that case. Second one is, let's say you didn't know displacement, which is a pretty big thing, I admit, but there's going to be one equation for each of these, and I'll actually write them down. So without acceleration, without displacement, without time, without let's see, and without the two velocities, either initial velocity or final velocity. And as you can see, there's no a in this equation, but there's all the other variables in that equation. So that's why the only variable missing is a. We also have without displacement, which gives you the final velocity is the initial velocity plus the acceleration times delta t. Again, this is very similar to this equation. It's saying if you move this initial velocity here, you get change in velocity is going to be acceleration times delta t, which means when you divide by delta t, you just get acceleration as the change in velocity over change in time, which is the definition of acceleration. The reason why we're not writing change in velocity here instead of having them on separate sides of the equation is because, first of all, there's no quantity that just says change in velocity. Like displacement is a quantity that represents the change in position, which is why that's a variable. However, there's no quantity, like there's no name for change in velocity. And also, we want both final velocity and initial velocity because they're important and they both are two of the variables we can use. Okay, without time, we have final velocity squared is equal to initial velocity squared plus 2a times delta x. Pretty interesting formula, usually used in 2D kinematics when we're talking about final velocity, but we haven't gone there yet. So without initial velocity, we have delta x is equal to final velocity times time minus 1/2 at squared. I'm not going to talk about that yet. I'll get back to that in a second. But then we also have, with that final velocity, it's delta x is equal to initial velocity times time minus 1/2 at squared, or plus 1/2 at squared, sorry. Now, this fourth equation is barely used. I don't think Mr. Becker even told you about it because it's not that common. In fact, the only reason I included it was for sake of completeness, because it's the one variable that is in every other equation. So I just wanted to include this because it's the one equation without initial velocity. But feel free to ignore that if you want. Could be useful in some cases. You're not given initial velocity, but it's barely ever used. So these are the 6 kinematic equations. And I'll go through, I'll actually go through a 2D kinematic problem using these equations, since that uses multiple equations in one usually, and 1D kinematic problems are relatively simple when compared to the 2D. So that's actually it for 1D motion. There were some other things that were covered, I believe, like stopping distance and intervals and things like that. But this is the core of physics. It's just a review. So for 2D motion, first let's talk about vectors. A vector is basically a quantity with both a magnitude or length and a direction. So this, even if they have the same length, they're different vectors because they have different directions. You usually use bracket notation for vectors, like a comma b says it is a horizontal, b vertical. The magnitude of vector is given by this. It's like 2 absolute value bars, or sometimes even 1. So this is called v, and it has this little arrow symbol on top. And this is going to be the square root of a squared plus b squared, where a and b are the horizontal and vertical components, respectively. Now, what about the direction? The direction is going to be equal to the inverse tangent of b over a. The reason why is using a little bit of trigonometry. If you construct this into a right triangle, you see that this is the angle we're looking for. That's called the direction. And inverse tangent uses these two sides, opposite over adjacent. Opposite would be b, adjacent would be a. So yes, it does work. And same thing for magnitude, actually. You use Pythagorean theorem on this right triangle, a and b. So the length of this is going to be square root of a squared plus b squared. Two more things are components, horizontal and vertical components. Let's say you know the magnitude and direction, but you don't know A and B. A is going to be equal to the magnitude of the vector times the cosine of the angle, because it's the adjacent side. That's the horizontal component, is the adjacent side. So it's going to be cosine. And then B is going to be, as you might imagine, the magnitude of the vector times sine theta. So now we can finally get into 2D motion. This is basically all you need to know about vectors for now. 2D motion uses the exact same formulas as we learned before, except there's also another set of formulas that just uses y instead of x. And then you have to specify vix or viy to show the horizontal or vertical velocity. But I won't rehash myself there by writing all the equations again. Just refer to this slide if you want to see the equations, just modify them for 2D kinematics. So like I promised, I'm going to do a practice problem about 2D kinematics. This one is actually going to use multiple equations. So it is a good problem to look into. I'm actually going to give you a few minutes to think about it first, and then I will explain the answer. And it will likely include decimals because it's not that nice of a problem. So you might want to use a calculator. So if you throw a ball, and let's start relatively easily. You throw a ball this way, straight horizontally. And obviously, I'll explain all this later. I'm just giving you a practice problem before I explain it, so that I use this practice problem to explain the work. Let's say you throw a ball with a velocity of 10 meters per second. It hits the ground it hits the ground 50 meters away. What is the final vertical velocity of final velocity in general? I might have given it away a bit at that, but the final velocity of the projectile or the ball. So feel free to pause here and see if you can do it yourself. But I'm going to go through the solution right now. It uses multiple kinematics. First of all, I'm going to explain a few concepts here. In 2D kinematics, you always have to split into horizontal and vertical velocities. So in this final position here, you're going downwards is the final velocity, but the horizontal velocity would be this way and the vertical would be this way. At the start, you're actually you just have a horizontal velocity. You don't have a vertical velocity since you're just throwing it forward. At some point in the middle, you have some amount of horizontal velocity and some amount of vertical velocity. So it changes depending on position. Now, one thing to note is that the horizontal velocity stays the exact same no matter what. Why? Because there's no horizontal acceleration. There is vertical acceleration though, and we can see that because it starts off with no vertical velocity and ends up with a lot of vertical velocity. So there is vertical acceleration, but what's providing that? Gravity. Gravity is going to provide, or the gravitational acceleration is going to be approximately 9.8 meters per second squared downwards. Good thing to know for problems like this. So based on that, we can solve this problem. First of all, we have a horizontal set of equations. We know that the velocity is 10 and we know the distance is 50. Is there acceleration? No, there isn't, because we just said there's no horizontal acceleration. So we can use the equation displacement is equal to velocity times time. And we have 50 is equal to 10 times time. And therefore, time is 5 seconds. It takes 5 seconds for the projectile to land on the ground. Now, how can we use that to find the final velocity? Well, first of all, let's find the vertical displacement. We use delta y is equal to, and we cannot use this equation because there is acceleration due to gravity. So we use initial velocity times time plus 1/2 at squared. And now we plug in our values. We know initial velocity is 0. Initial vertical velocity is 0 because you just start off with a horizontal velocity. So this entire term is 0. And then we have just 1/2 times negative 9.8 since it's downwards. And then time is 5. We found that out. Squared. And we're going to get our vertical displacement. And it's actually going to be a negative number. The reason why is because we said acceleration downwards was negative. So the general coordinate frame we use is upwards is positive and downwards is negative, which is why the acceleration and displacement are now going to be negative. We get negative 122.5 meters. What can we do with that? We wanted the final velocity, not the final position. So we use yet another kinematic equation, which is why I really like this problem. You use a lot of kinematic equations. V final squared is equal to V initial squared plus 2a times delta y in this case, since we're talking about vertical. We have final velocity squared is going to be equal to initial velocity was 0. We can take that out. It's just going to be 2 times negative 9.8 times delta y, which was negative 122.5. And now the negatives cancel out, and we get V final is going to be equal to the square root of 2 times 9.8 times 102, 122.5. And that is going to give us exactly 49, which is very interesting because when I gave you this problem, I did not plan to have nice numbers involved. So it's interesting that the exact square root will be 49. Pretty nice. So it technically is negative 49 since we said downwards is negative and the velocity is moving downwards. So it is negative 49. Best to keep that. Now, is that our answer? No, because I did clarify at the beginning of the problem, I wanted the final velocity, not the final vertical velocity. So we have to do vectors. We know the horizontal component of velocity never changes because no acceleration. So we know it's still 10. And we know the downwards is 49 because we just found that, or negative 49. But since we're going to do square root of 10 squared plus negative 49 squared, the negative doesn't really matter. This is the formula for the magnitude, which is what we're trying to find. And we get square root of 10 squared, which is 100, plus 49 squared, which is 2,401. We get square root of 2,501, which is approximately 50 meters per second. And this is where the nice numbers end because it's not exactly 50. It's 50.0099999 and so on. But it's close enough to 50 that we can round it to 50 meters per second. So that means that the total magnitude is going to be 50, and we can actually find the direction of the velocity as well. I didn't clarify that I wanted that, but since it is a vector, we can find the direction. However, I'm going to introduce one other type of projectile motion, and then I'll talk about forces. With the other kind of projectile motion is where it starts off with both the horizontal and vertical velocity, and then goes back down. The reason why this is important is because we cannot directly assume that the initial velocity is the initial horizontal velocity. It's the vector component of both. So we need both the initial velocity and the angle it was launched at to find both components, and then we can use the same kinematic formulas. Okay, now forces. Forces are always fun. There are a few types of forces. So we got the gravitational force. We said earlier that there's a gravitational acceleration. So the gravitational force is basically for anything that has mass, Fg is said to be mg. The value of it is mg, where g is the gravitational acceleration, or the gravitational field strength, which is 9.8 meters per second squared if you're talking about gravitational acceleration, but it has different units if you're talking about the field strength, and I'll get to that in a minute. We also have a few other types of forces, but before I do that, let's talk about forces in general. The unit for forces is newtons, and named after Isaac Newton, who made his famous three laws of motion, which we will cover. But that's why the gravitational acceleration would be newtons per kilogram for the gravitational field strength version of it. Both have the same values, just different units for different cases. Now, what other forces do we have? There's the normal force upwards, or it's not always going to be upwards. The force of gravity will always be downwards no matter what. Force of the normal force will be perpendicular to any other any surface. So if you have a flat plane, gravity goes downwards, normal force is upwards. If you have an inclined surface, gravity goes directly downwards, but normal force is perpendicular to the incline. And if you have something completely vertical, gravity goes downwards, normal force is perpendicular. So there are a bunch of different versions of that. There's also tension force, which is whenever you have a rope or string or cord of some kind, you have a tension force that is like a pulling force. And then we have frictional force. There are two kinds of friction, kinetic and static. Kinetic friction is when it's actually moving. Static friction is before it starts to move. And in general, friction prevents motion. There are some rare cases when it actually allows motion, but I won't get into that. Now, the normal force is abbreviated Fn, and tension force Ft, as you might imagine. The FFK, kinetic friction, and FFS are two types of friction, and they each have formulas. So the kinetic friction is easier to start off with. There's something called the coefficient of static friction, the coefficient of kinetic friction. And for kinetic friction, it's mu k. This is the mu symbol, and it's basically the coefficient of friction. That is an experimental value that is probably provided to you in a problem, or it's something you're asked to find. It's not something like a formula you can use on different applications. Times the normal force. The reason why it's not the gravitational force is because the normal force is not always equal to the gravitational force. On a flat plane, yes, it is, because the object is not levitating upwards, so it's equal to each other. However, on an incline, gravity and normal force are not always equal to each other because the vertical component of the normal force would be equal to the gravity, but the entire normal force would not be. So yeah, it depends on that. And then there's FFS, static friction, which is actually less than or equal to the coefficient of static friction times the normal force. Why less than or equal to? Because it's possible that it's less than. So basically, you have like a tension force pulling a sled, and it's not moving, and that's because the static friction is varying. Now, what happens if you're pulling some amount, and when it's equal to this, basically the normal force times the coefficient of static friction is like that. That means it'll move backwards because which is something I'll get into later, net forces and acceleration and whatnot. But realistically speaking, if you had a diagram like this, you would obviously imagine it'll be moving that way. But if you're pulling on a sled and it doesn't move, it doesn't also move backwards. Let's say it's this is the combined static force, and you are exceeding that. Then it moves this way. What if you're exactly that? Well, then it doesn't move at all. So what I'm trying to say here is, if it's less than this and it doesn't move here, there must be something else involved. And the reason why is because that's why we put the less than or equal to. It matches the force that's being applied. If it's this tiny, the static friction is this tiny. If it's that big, it's that big the other direction. And then if it exceeds it, that's when it's not static friction anymore, and it's kinetic friction trying to slow it down. So this basically changes until there's the FFS max, the maximum possible static friction, which is directly equal to the static coefficient times the normal force. All right, finally, we get into net force and things like that. Net force is basically going to be the sum of all forces on an object. So gravitational force, normal force, and then friction force, tension force, a bunch of other forces. Now, why is that important? Because it helps us understand Newton's three laws of motion. The first law of motion is that if there is no net external force, then the object does not change its motion. That's a simplified version of it. It's basically saying the object does, if the object is originally moving, it continues moving with that same velocity in that same direction. And if the object is originally sitting still, it continues sitting still if there's no net force applied. Keyword net force. There could be a gravitational force and a normal force on an object just sitting still, but it's not moving because there's no net force since those two forces cancel each other out. There definitely is a force and multiple forces on that object, but there's no net force causing it to accelerate. Speaking of net forces causing it to accelerate, Newton's second law of motion says that F equals ma. It's probably the most common one. Basically, a force causes an acceleration, and the quantity or the value of that acceleration is equal to the force divided by the mass of the object. This is another way of saying it. F over m equals a. And truthfully speaking, this is not exactly what Newton's second law says. It has something to do with momentum and impulse, which we will get to actually in second semester, but it can be translated to say F equals ma. And then Newton's third law of motion, also pretty famous, the action-reaction pair law, basically saying if there's a force applied on an object, then that object applies a force of equal magnitude and opposite direction to the first object. So if you have two trains that crash into each other, you have the first train exerting a force on the second train and the second train exerting an equal but opposite direction force on the first train. What happens if there's a very small train and a huge train? Or think of it as an even more extreme scenario. You're driving on the freeway and a bug hits your car. The bug is applying a force to you and you're applying a force to the bug. But the bug just completely stops moving and is like dead probably. But you just continue moving with the same velocity. You don't even care if you hit the bug. But aren't we supposed to apply equal forces to each other? Yes. And that's where Newton's second law comes in. The forces are equal, but the mass of the car is much bigger, meaning the net acceleration of the car is very, very tiny. If the force was 10 newtons, which is very big for a bug hitting a car, and the mass of the car is like 1,000 kilograms, it's going to be a very, very, very small acceleration. It's going to be 0.01 meters per second squared, which does not really change much for the car. But the bug, it's like 0.1 kilograms, if even. Again, this is a very big bug. That's going to be 100 meters per second squared, which is a completely huge amount of acceleration for the bug. So it depends on mass. The same force is applied, but that doesn't necessarily mean the same acceleration is applied. That's probably the main part of forces you need to know. Free body diagrams is actually what I was drawing up here. You have a dot, and then you have all the forces applied. So let's say there's Fg downwards, Fn upwards. There's a frictional force here and an applied force here, causing it to move in that direction overall. That's an example of a free body diagram. You obviously have to label the different parts. So Fa for applied force, Ff, K for kinetic friction, since it's moving this way, we already established that, and then Fn for normal force. And that's it. That's all we have for the semester 1 physics review final. I probably skipped a few things here and there, but I just wanted to cover the main things and make the video not too long to watch. So good luck for your finals.